So the second sum, hopefully you got to be a 0, right? 1 plus a negative 1. If I do the first 3, then we add a 1. The first 4 bring us back to 0. And then the fifth sum brings us back to a 1. What we are now looking for is, as we move down our partial sums here, are these sums converging upon a particular value? No. So you would say in this case that this diverges. Right? These are not converging upon a particular sum. All right. For number 2, the first sum is the 3/10. You might want to think of this as decimals too as we do these partial sums. So 0.3. The next sum, wouldn't that be 0.33? Let me write this as 0.3. The third sum, do you need a packet, Alex? Do you need a packet?
Yeah, I need one.
There's some up there. I think it's right on top by the left. If I add up, so this was a 0.03. Yeah, unit 10. And then this will say 0.003. So isn't that now 0.333? What we should then kind of understand as we're looking at this, that this does kind of approach a ceiling, is approaching a limiting value. And we would be converging. What is this as we go further and further down? We're just going to get closer and closer to what? 1/3. So this does converge, and it converges to 1/3. All right. Just because it's an infinite sum doesn't mean that we can't converge. We just showed right here that we definitely still have a sum. All right, number 3, same thought process. S sub 1 is a 2. Our second sum is 2 plus 2/3, so write 2.6. Just put a bunch of 6s just so you can kind of see how this is going to play out in a minute. And then 2/9, anytime like 2/9, 3/9, 4/9, that just gives you that number repeating. So this is 0.2 repeating. So if I start adding 0.2s to all of these, notice how we'll get like 0.8888, all of these guys. 2/20, I gotta recall this one real quick. 2/27, 2 divided by, gives you 0.074074, so on and so forth. So add 0.074, so on and so forth. Let's say it was 2.95 and some change right here. As we now look at this, we went from 2 to 2.6 repeating, 2.88 repeating, 2.95. What does this appear to be converging to?
3.
Yeah, this converges to 3. That's our ceiling. We would just, if we continue that pattern, continue to get closer and closer and closer to 3. Part of this chapter is this, and we'll go back now that we've done this. I gave you the general term here. This general term gave us the first 3. We'll go back to number 1 and do this as well. Write a general term for this now. So if I ask you, what is the a sub n term, what would that be? That's creating a 2, and then a 2/3, and then a 2/9, 2/27, so on and so forth. All right, sometimes people see these quickly, sometimes they don't. We get that. Yeah. 2 over what?
2 over 3 to the n.
Good. 2 over 3 to the n. We can play games with this little n minus 1. Eventually, we'll start talking about, let's put the little sigma in front of it because it's a sum. And then depending on where your n starts, so if we use Megan's, we would want n to be a 0, right? So that we start with the 2. If you put an n minus a 1 here, you could actually let n be a 1. There's a lot of games we could play. I like Megan's. We're going to go with that one. We'll assume that the nth term is, the initial one is the 0 term. And then this should start spitting out all of those values, all right? All right, last one. All right, first sum is a 1. Second sum would be a negative 1. Let's actually graph these out a little bit too, just so you can see, because this, now they're going to bounce back and forth between positives and negatives, at least for a little while. So first we're at 1, and then the second one is at negative 1. So then the negative 1 plus a 4 is a 3. So the third one is up here at 3. Fourth one, we then do 3 minus that 8, which is a -5. So now we're down here. So even though we're bouncing back and forth, positive, positive, or positive, negative, positive, negative, as we plot these on a graph, does it appear they're converging to the same value? No. All right. Isn't this one looking like it's just going to get bigger in a positive direction? This is going to continue to get more negative. So this guy, we would say, diverges. All right, go back to number 1 real quick. Let's write this. I'm going to write this as a -1 to the nth power. That's the general term for that. Then we have all of these general terms. General term here, 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 and this one diverged, and then that's our general term there. All right. Go down. I'm not sure if we talked about these now or not. The idea of a geometric series, you certainly dealt with geometric sequences and such. These are a series, and numbers 1, 2, 3, and 4 are all geometric series. All right, every single one of them, because each term, this you should know, is obtained from the preceding term through multiplication. We remember endlessly in Math 1, geometric versus arithmetic sequences and all of that stuff. So geometric is you continue to multiply to get each subsequent term. That term for what we're going to deal with, we're going to call R, because that's, remember, you would call it a common ratio versus common difference. We have a common ratio. So if I go to the first one, number 1, if I look at that common ratio, what were we multiplying 1 by to get a -1, and then back to a +1, -1, +1? Whatever that is, what we're calling our R. So in number 1, when we all agree, we were multiplying by a -1 each time. All right, so that's our common R. So number 2, if we pop up to number 2, the numerator remained a 3 all the time. So the numerator, we would have had to have been multiplying by a 1. And then to go from 10 to 100, 100 to 1,000, so on and so forth, we would hopefully see that that was a 1/10. Number 3 is what? 1 over what? 3. So our ratio there is 1 over 3. And then number 4, what we were multiplying by to go from 1 to a -2, and then to turn a -2 into a 4, 4 into a -8 would have been a what? -2. Then next to these, right in number 1, remember how that one diverged? Number 2, that converged. 3 converged. And 4 diverged, because the R's are going to indicate whether these converge or not. So we want to now look here in this next little thing here. Why did these couple diverge, and why did these couple converge? Okay, so as we come down here in a geometric series, again, this is our initial term, and then we start multiplying by R the first time, and then another time, a third time, and that gives us our series. So that's how we can write this. Whatever the initial amount is, multiplied by that common ratio to the n or n-1. It kind of just depends on where we started. Since I want a to be my first term, and I have n-1, we're going to start at a 1. What this is then telling you, the sum of a geometric series should equal, it's going to converge to a sum, and that sum is always going to be the a over 1 minus r. Notice what a is, because we're going to add one little element to this. Notice how a is the very first term in our series of numbers that we're adding. So we're going to just put this as an a sub 1 for future reference, so it's easier to kind of understand what that is telling us. Did we do this still? Is this something we've seen before? Maybe. This guy? The a on the left side. Oh, sum. Sorry, Brian. That's just a fancy U. Let me write it more traditional. There. Sum. That's right. Yeah. Oh, okay. Yeah. Sum. There's no. I started writing in yellow before it changed. All right. Yeah. Now every S looks like an integral. All right. So this is our sum, and it's going to converge only if. So we are going to converge to this sum if the absolute value of your ratio is less than 1. So go up here to numbers 2 and number 3. Our ratio was a 1/10. Isn't its absolute value less than 1? And we converged. If you look at number 3, the absolute value of our ratio of 1/3 less than 1, and it converges. However, you're going to diverge if the absolute value of your ratio is greater than or equal to a 1. That's number 1, right? The absolute value in number 1 equaled 1. That's why that one ultimately diverged. And then number 4 diverged because the absolute value of a -2 is greater than 1. That's how we're going to know if this diverges or not. So the only way a geometric series could converge, if we know it's a geometric series, is if your common ratio falls within this interval of a -1 to 1. That's it. And then you're going to hear a lot of this in this chapter. This is what we call an interval of convergence. As long as R fits within that window, our geometric series is going to converge. Okay? And if it does converge, we can find that sum by using this guy over here. And that is, by and large, what we want to deal with here of these next couple of pages, at least the next page. All right. So first thing you're going to do in these sets of problems, just determine first and foremost if the following series are going to converge or diverge. So if we look at that, what that really means is identify what your common ratio is. So if I start at 2, go to 2/3, to 2/9, to 2/27, so on and so forth, we want to first identify that ratio. Should look familiar, right? All right, so then we on the previous page say, because we already did this problem, our ratio was a 1/3. This should converge. And we know what it converges to, right? So this is, where is it? This problem right here. So this better converge to 3. So if we now use our fancy little formula to make this a little bit easier, what we said is the sum should equal the first term in our series divided by 1 minus that common ratio. The first term is a 2, and then I would do 1 minus a 1/3, so that this gives us 2 over a 2/3, multiplied by that reciprocal there, so that the 2's ultimately cancel, and voila, it's the 3 that we got on the previous page by writing them out, adding them up. Okay. 6, we did this one as well, correct? This one we said had a sum of 1/3, so this better show out to be a sum of 1/3. So we're going to know it converges because our ratio would have been 1/10, so it's less than 1. If I now ask you to find the actual sum, instead of having to write them all out and add them all up, even though this one is pretty simple, we could just do the first term of 3/10 divided by 1 minus that common ratio of 1/10. So we get 3/10 on top. This would give us 9/10 on the bottom. 10s cancel, leaving you with 3/9, which is in fact the 1/3 that we got on the previous page as well. All right. So these were the 2 that converged, so those should have worked out nicely. When we get to number 7, this is the one that did not. So here's where this chapter gets really interesting and where people have the hardest time. When something diverges, and you're going to have to, even sometimes when they converge as we move along, you need to not just write diverge, we have to write a quick little justification for that. All right? We want to be succinct, we want to be specific. So what we would simply write here is that we are looking at a geometric series with a ratio whose absolute value is, we'll get to that part, and the absolute value of that ratio is 2. And then what you need to show then is which is greater than 1, because the absolute value has to be less than 1. You're going to do all these little justifications over the next 2 weeks. That's the very first one. Geometric series with a absolute value of our ratio equal to 2, and it's greater than 1. That's why we diverge. So if we go to number 8, first one we haven't done already. So identify what your R is. That's kind of the first thing we need to make sure we do. All right, based upon our ratio, what you think your ratio is, should this converge? No. All right. Nick, what did you get for the ratio here?
I got pi over 2.
Me too. So pi over 2 roughly is about 1.5-ish. That's greater than 1. So we would say that this diverges. And again, you need to state the type of series because as we move along, they're not all going to be geometric series. Even on the next page, they'll stop being geometric. But right now, this is a geometric series. And this guy has a ratio whose absolute value is 1.5. And that is greater than, not a 0. That is greater than a 1. Okay, number 9. Notice now how what I have done. Instead of listing out the first 3, 4, 5 terms, I'm giving you the general term. So what I would strongly suggest early on, and I promise in about 2 weeks you won't have to do this, but early on as you get used to these, I would strongly recommend actually writing out the first 3 or 4 terms so you can see what the first term is. You can see what that common ratio is. Eventually you'll do enough of these where that won't be a big issue. But I would list these first few. So let n be a 0. So that means I'm going to get a positive 1 in the numerator. I'm going to get a positive 1 in my denominator. So that's the first term. If you let your n be a 1, I'm going to get a negative 1 in the numerator. And I will get 4 to the 1 in my denominator. So negative 1/4. Usually 3 is good enough to kind of see the pattern. If I let n be a 2, I'm back to a positive 1. And then I'm going to get a 16 in my denominator. So with that, if we continue this pattern, identify what r is, and then based upon that, we know if it converges or diverges. If it diverges, we're going to say y. If it converges, we're going to find the sum. All right, what is our r? Negative what? Good. Negative 1/4 should be our r. That absolute value is less than 1, so we should be saying this converges. And then we need to identify what does it converge to. That's our sum formula, where we're going to take the first term, divide it by 1 minus that common ratio. So the first term here is a 1. We would do 1 minus the common ratio is a negative 1/4. So that gives us 1 over 5/4. So what this should converge to is 4/5. So if you were to go to your calculator and just start adding, every once in a while people like to do that. We don't believe it. You should start to converge upon the value of 0.8. Each successive time, you get closer and closer and closer to 0.8. All right. Do 10. At this point, usually people start catching on pretty good. I'd write it again out the first 2 or probably the first 3 is usually good enough. And if you're already kind of seeing how is this geometric, how can I get my first term, know what my ratio is, you can jump right to all of that. And that's eventually what we want to graduate to anyway. So the sooner the better, but if not, write the first 3 of those out. All right, so when you did that, first term would have been a 1. It's not showing up good here. There we go. If n is a 1, you're going to get 3 over 5. If you're going to square those, you're going to get 9 over 25. All right, so from there, Safian, what is our ratio here?
3 over 5.
Good, 3 over 5. That absolute value is smaller than a 1, so this should converge. And we're going to do our first term of 1, and then 1 minus that common ratio. Is that 2/5? So what we would then say, hopefully if you had this, is that this converges to 5 halves. Or if you throw it into your calculator and want to see a bunch of decimals, they're going to get closer and closer and closer to 2.5. Okay. All right. Yeah, let's do this one. That's another one that's alternating. So if I let my n be a 0, it's going to be positive initially, and then I would get 5 over 1, because I get 4 to the 0. If your n is then a 1, now it's going to be negative, because I'm going to get negative 1 to the power of 1. So I'm going to get a negative 5, and then 4. If n is a 2, now I'm going to be squaring the negative 1. So now it's going to be positive again, 5, and then 4 squared should be 16. From there, we should be able to see our ratio if we continued this pattern. Notice how we're positive, negative, so we're multiplying by a negative, and then in the numerator 1, and then your denominator of 4, so negative 1/4. We also want to kind of start recognizing, now that we've done 3 or 4 of these in a row, notice how we're getting, what's our ratio, what are we constantly multiplying by, because we want to eventually be able to just look at this thing and know what our ratio is, okay? All right, so do your sum. First term would have been a 5 over 1 minus the negative 1/4. Yeah. So what is that, 5/4? So very nicely, this one should converge to 4. Writing the word converges is important, because we never actually get 4, right? It just becomes 3.9999, or bounces back and forth actually, but you'll just get closer and closer and closer to 4. All right, the next one is a little bit different. So when you are going to be doing these, what you don't want to do, we don't want to actually do the first term as 5 plus 1, because these would both become a 1, and then do 5 halves plus 1/3 and add those up. These are not, the sum of those are not going to show what we want in terms of if these converge or not. So what we want to do with these, it's similar to integrals, and really all integrals are sums anyway with these sigma signs. We really want to turn this into 2 separate problems. So we want to find whether or not the first one would converge. If it does, since these are being added in the original problem, we would add it to whatever the second one would converge to if it converged. If either of these diverges, it doesn't matter if the other one converged. Because let's say the one had a sum of 3, if the other one is going to infinity, then you're still going to diverge overall. So for the first time, let's not write these out. Try not to write them all out. So now we have 2 of them. So see if you can just look at this one. If we've done enough to identify what would your ratio be here, what would our ratio be here? If you need to write them, don't not do it in the future, but just for this first time, see if we can kind of figure out what that is without having to do all that extra work. All right, what would that first ratio be? Good. How'd you get there?
The denominator is always going to split it.
Good. So what we're hopefully starting to recognize, whatever is getting raised to the nth power, so here it was just the 2 to the nth, isn't that what we are repeatedly multiplying by? If we go back to the previous problem, the denominator was raised to that nth power. Weren't we multiplying each denominator by a 4? The previous one, I think it was, both of them were. So since both the 3 and the 5 are raised to the nth, the numerator was multiplying by 3 every time, the denominator was multiplying by 5 every time. So as we move along, we kind of want to understand, that's how we can really determine what our ratio is, what we're multiplying by. So aren't we really just multiplying the second one by a 3 in the denominator over and over and over again? So this ratio should have been a 1 over a 3. So these should both converge. So for the first one, the sum of that first one, hopefully we can do this in our head. If n is a 0, I would just get 5 over 1. So that first term is a 1. And then I would do 1 over 1/2. So the sum of the first one was what, 10? So that one converges to 10. If I come over here to the second one, the first term, if n is a 0, so if we plug in a 0 into this term, the first term is a 1. And then I would do 1 minus the ratio of 1/3. So the second sum is 1 over 2/3, which is 3/2. They both converge. So then your overall answer is the sum of these. So we would ultimately say as our final answer, as this converges to 10 plus 3/2. You can write it as 11.5, however you want to do it. 23/2. Yeah, Lily. So if I did 5 divided by the 1/2. Remember your little trick you showed me? Yeah. So do that, and then that should give us a 10. All right. Okay, one more real quick. We'll probably stop with this one anyway. Do 13, see what you think. Maybe we'll get into another one. All right, and should this converge or diverge? Diverge, because what's our ratio? Root 2. So you have to kind of have an understanding of what root 2 is, but clearly root 2 is greater than root 1, right? And root 1 is a 1. So root 2 has to be greater than 1. So the fact that your ratio is a 2, we haven't had to do one here in a little bit. This is one of the ones you're going to have to say diverges and then explain how we came to that conclusion. So we still have to, even though we haven't done anything other than a geometric so far, we will in due time. So put what type of series we're looking at first, geometric. And then we say, here's the issue with this geometric series and why it diverges. The absolute value of its ratio is a root 2, and that is greater than 1. That's why it would diverge. Yeah.
I don't know if you said this already, but would it be true that like our R would always be like n to, or if n was equal to 1, that'd be our term?
Say that one more time now.
So would it be true that like R would equal our term if n was equal to 1?
R would equal R.
So like for this one, if n was equal to 1, it would be
This n right here?
Yeah.
Say that again now, one more time.
If n equals 1,
Right.
in this case, then it would be root 2, and then that would be our R. And then the last problem would be, I guess, kind of the same thing.
Yeah, I mean, it wouldn't necessarily matter what the n is, because even if I start at 0 here, just this being
So it
2d.
seems like if it was like a quicker way to find R, just like put n equal to 1, and then that would be it. Like, would that always be true?
Yeah, I suppose, because even if this is an n minus a 1, no, I wouldn't say that, because what if this is n minus a 1? If I now let this plug in, wouldn't this evaluate to be a 1? And then our ratio wouldn't be 1, it's still going to be that root 2. Okay, so yeah, no. Okay, bring this tomorrow. We got definitely the next page you're going to need to see. So bring this tomorrow, we'll wrap this up and then see where we're at. Say that again? No, just, I'm kind of, you guys might just have an early,